paper is by Professor Changyu Xia from University of Brasileiro. He will talk about Hardy and Rellich type inequalities on remaining manifold.
Okay, I would like to thank the organizer, especially to Professor Tan, for the invitation to give a talk here. So what I want to talk is about Hardy and Rellich type inequalities on Riemannian manifolds. Now let's begin with the following problem. If we have a complete non-compact manifold, we want to find conditions so that M has simple topological type. So there are many results about such a problem. So let's recall some results and then look at what we want to see. So this is the so-called Chig-Gromov-Soule conjecture proved by Perlman, which states that if the sectional curvature of a complete open manifold is non-negative and positive at one point, then it's, this manifold is diffeomorphic to a Euclidean space. Another result is Chig-Coding, which states that the volume growth of the geodesic balls looks like very much the volume growth of the balls in the Euclidean space. Then the manifold is diffeomorphic to a Euclidean space when the Rich curvature of the manifold is non-negative. Then let's look at another results. So we have the definition of the ray densities. So if we let Rp be the set of rays starting from one point, and then we define this function, this Rpr to be the intersection of this set with the sphere of radius r, and then we define two functions here, h and r. These two functions give some information about the rays of the manifold. So it's a way to measure the ray on the manifolds. In the Euclidean space, we have many rays. Any geodesic is a ray. Then we want to have a comparison of these manifolds, the rays in a manifold with the Euclidean space by these two functions. Then when we use these two functions, one has the following results. For example, Shim proved that if this function has a limit which is less than this fixed number, then the manifold has a finite topological type. Finite topological type means that the manifold outside a compact set is homomorphic to the boundary of this compact set and the half line. Okay? And then if we assume that the sectional curvature of the manifold is non-negative, and this condition, either this condition or this condition is satisfied, then the manifold is diffeomorphic to the Euclidean space. Okay? So these are some examples of manifolds with the conditions to ensure that they are close to the Euclidean space. So these conditions, usually we have the curvature condition and the geometric condition. This is the geometric condition. Here is also a geometric condition. Yeah, okay. This is the curvature condition, but the curvature condition is very strong. Okay. Then one can also consider the analytical condition, curvature condition plus analytical condition to obtain some result. For example, the Cheeger-Cody mini-course theorem states that if the Ricci curvature of a non-compact open manifold is non-negative, and if the space of linear closed harmonic functions has dimension m+1, this manifold is isometric to a Euclidean space. Okay? So another interesting result is related to the Sobolev inequality. Let's look at the result. The Sobolev inequality states that for any function with a compact support in the Euclidean space, this inequality holds. And then Ledoux proved that if a complete open manifold with a non-negative Ricci curvature on which the Sobolev type inequality holds, then the manifold is isometric to the Euclidean space. Okay? So this is the curvature condition plus the analytical condition on functions. Then a natural problem is to consider other kind of inequalities, other kind of Sobolev type inequalities. So this is how about the structure of complete open manifolds supporting some other kind of Sobolev type inequalities. So in order to answer this question, we need to know what kind of other kind of Sobolev type inequalities on the Euclidean space hold. Okay, so let's list most of the Sobolev type inequalities on the Euclidean space. So firstly, the sharp constant in the Sobolev inequality has been obtained by Alban and Tarrant in 1976, which is given by this number, and this number is achieved by a family of functions of this type. Okay. So this is the so-called log-Sobolev inequality, which was proved by Gross in 1975, which states that for any function with a compact support and with the integral 1 of the square of this function, then we have this inequality. This is the so-called log-Sobolev inequality. Okay. This is the any log-Sobolev inequality, which states that for any p in this interval and any function satisfying this condition, then we have this inequality, and the best constant Lmp in this inequality is achieved by a family of functions here. We have another inequality called Nash inequality. Nash inequality was firstly proved by Nash in 1958, which states that for any function with a compact support in the Euclidean space, this inequality holds. And the best constant here was computed by Karl and Rose in 1999, which is given by this number. Here, number 1, Bn is the first non-zero Newman eigenvalue of the Laplacian of this unit ball in Euclidean space, and omega n is the volume of the unit ball. Okay. So another family of Sobolev type inequality is the so-called the Cavallari-Kroneberg inequality. The Cavallari-Kroneberg inequality is a family of inequalities, contains many inequalities. So if we have numbers n, a, b, p, satisfying these conditions here, then this inequality holds. And the best constant was obtained for the case A equals to 0 and B between 0 and 1 by nearby, and for the case A non-negative, B in the interval A plus 1, the best constant was computed by Changyu, and the functions here achieve this best constant. Okay. We have also some other kind of inequalities called Gagliardo-Nirenberg inequality. The Gagliardo-Nirenberg inequality contains here on the right-hand side has two parts. And the best constant here was computed by Del Pino Bauch in 2003, and the minimizers for this inequality is a family of functions here. Okay. And then let's see another sharper Kavalertic-Nirenberg inequality. So the Kavalertic-Nirenberg inequality here is another family of Kavalertic-Nirenberg inequality, which stays here, and the sharper constant was obtained in 2007 by me, and the best and the functions which attain this best constant is given here. And this is the so-called Harding inequality. Harding inequality. The Harding inequality, we look here, this is the norm of the position vector. So the Harding inequality contains the norm of the position vector here, and then the functions u lambda x realize the inequality, the equality case here. Here is the so-called generalized Hardy inequality obtained by Rellich in 1997, which contains the Hardy inequality and has more things here. So this is given here. This is the so-called affine Sobolev inequality obtained by Luthvard Yan Zhang in 2002, and there are many work following this so-called affine Sobolev inequality, but for the time being, we have no result about the implication of the this kind of affine Sobolev inequality on the manifold about 2D topology of the manifold. So is so this is the, and then we look at the problem when the manifolds admit some Sobolev type inequality. What can we say about the topology or the geometry? We come back to our problem before, and considering a manifold which supports some Sobolev type inequality, and then we talk about the some result. Okay, so the first result is the so-called heat color bounds. So on a complete manifold, the Sobolev inequality or the log Sobolev inequality or the Nash inequality are all equivalent to a common upper bound on the heat color. And this is, says that these three inequalities are all equivalent. See one inequality holds, and then other two inequalities also hold on the manifold. So this is, for example, we can say more things now about the Sobolev inequality. The Sobolev inequality 3.1. Now this inequality holds on a complete minimal submanifold of a Hadamard manifold, and so the inequality 3.2 and 3.3 also hold on them. Okay? Also, a result by Berkeley Concord, the dogs states that if we have this log-Sobolev inequality, the hit kernel of the manifold has an explicit upper bound here. This upper bound is sharp. In particular, if the Rich curvature of the manifold is non-negative, then the manifold is isometric to the Euclidean space. Then we consider the other kind of Sobolev inequality that on a complete manifold or with a non-negative Rich curvature. So the starting point is the result by the dogs, which states that when the Rich curvature is non-negative and the manifold admits the Sobolev inequality, then the manifold is exactly the Euclidean space. And then we have we can prove a stability theorem for this and the Dogs theorem. This states that if we replace this constant here by a little bigger one, then the manifold is diffeomorphic to the Euclidean space. Okay? So with these two results in mind, it is natural to consider other kind of Sobolev type of inequality. Okay? Then let's look at some results. So on a complete manifold with a non-negative Rich curvature on which the Nash inequality is satisfied, then Delucci, Erbi, Vaughan proved that the manifold is flat, and then we proved that the manifold is exactly the Euclidean space. This is was conjectured by the Dogs. And then we consider the Cappelletti-Kohn-Liebenberg inequality. Now this is the a family of Cappelletti-Kohn-Liebenberg inequality. If also we have non-negative Rich curvature, if the Cappelletti-Kohn-Liebenberg inequality holds on the manifold, then we have an estimate on the volume of geodesic balls. This V0 R is the volume of a ball of radius R in the Euclidean space. Also, this estimate is sharp, since for the Euclidean space we have exactly the equality. So if we use this result and some other results, we can have topological information about the manifold. So let's recall the result by Peterly and Anderson, which states that if the Rich curvature of the manifold is non-negative and the geodesic ball has a volume growth similar to the that of the ball in the Euclidean space, then the manifold has a finite fundamental group. And if this number is close to 1, then the manifold is diffeomorphic to the Euclidean space. Then we use this result and the result before. We can show that the manifold has finite fundamental group in and the number of the fundamental group is bounded above by this number. And if the constant in the quadratic Nierenberg inequality is exactly the best constant, then the manifold is isometric to the Euclidean space. Also, there exists a small number such that if this constant is not very large, then the manifold is diffeomorphic to the Euclidean space. Then we look at some other kind of inequalities here. And this is the quadratic Nierenberg inequality, sharp quadratic Nierenberg inequality. If the manifold has non-negative rich curvature, also holds the quadratic Nierenberg type inequality with the best constant here in the Euclidean space, then the manifold is isometric to Rn. But unfortunately, it's still not clear if the manifold is homeomorphic or diffeomorphic to Rn. If this best constant is replaced by this a little bit one, a little big one. Okay. Then we consider the log Sobolev inequality. In the case of the best constant here, if we have no epsilon here, then a result before states that the manifold is isometric to the Euclidean space. Then Adriano and I proved that if we put an epsilon positive here, then the manifold is diffeomorphic to the Euclidean space. Now we consider the manifold with a asymptotically non-negative rich curvature. So this means that the manifold is almost has almost a non-negative rich curvature. Now look at the definition here. If we have a manifold complete, the rich curvature is bounded below by this function, but this function has integral not large. Then we say that the manifold has asymptotically non-negative rich curvature. Also, one can define the notion of asymptotically non-negative sectional curvature. As in the to the case of non-negative rich curvature, we have the Bishop-Gromov comparison theorem. Also, for the asymptotically non-negative rich curvature, we have a similar volume comparison result. Okay, so this is one can look at some book by City, or there are proof for this inequality. Okay. Then we consider a manifold with a asymptotically non-negative rich curvature, and we have some constants here satisfying these two conditions, and then we assume that the Gagliardo inequality holds on the manifold. Then we'll also have a long-bound estimate for the volume of geodesic balls. Also, Piccola Veronelli proved a similar result when a Sobolev type inequality holds on the manifold. Then we want to use this result to deduce some topological result for the manifold. In this case, we did some result about the critical points of distance function, and to recall a result by Zhu. This is the definition of a critical point about the distance function. And then in this definition, if we use this definition, the distance function in the Euclidean space only has one critical point. Also, has no critical point. I'm sorry. For the distance function in the sphere, it has only one critical point, which is the antipodal point. And then a theorem just said that if a manifold is complete, and if there exists a point which has no critical point, then this manifold is homeomorphic to the Euclidean space. And if there exists a point such that the distance function has only one critical point, then this manifold is homeomorphic to a sphere. So with the notion of a critical point of distance function, so Zhu proved that given a positive number, there exists a positive epsilon, such that if a complete open asymptotically non-negative sectional curvature manifold satisfies this condition, and the volume growth of the geodesic ball looks like this, then the distance function here has no critical points, and M is diffeomorphic, and so M is homeomorphic, has no critical point, is homeomorphic, and so here is homeomorphic. Then if we use the result of Zhu and the result before, we can deduce that if we have a manifold such that the sectional curvature is asymptotically non-negative, and the Gagliardo type inequality holds, Gagliardo type inequality 4.2 here, this inequality holds on the manifold, then the manifold is also here is homeomorphic to the Euclidean space. Also, we have a similar corollary. If we assume that the radial curvature is non-negative, the radial curvature is non-negative is stronger than the asymptotically non-negative sectional curvature. Then we consider the generalized Hardy inequality. We have also some estimates about the volume growth of the geodesic balls. Now, when the manifold has asymptotically non-negative rich curvature, then we have these estimates. Here, W is the best constant in this inequality when the manifold is Euclidean space. In particular, if we assume that the rich curvature of the manifold is non-negative and the constant C is close to W, then the manifold is diffeomorphic to the Euclidean space. And then, when we have some observation about the results before, this the above results tells us that the existence of a Sobolev type inequality, such as the Gagliardo-Nirenberg, the log-Sobolev, the Cavallari-Nirenberg, is such on a manifold with a non-negative rich curvature has strong restriction on the geometric and topological structures. So if we have a manifold with a non-negative rich curvature, which supports some Sobolev type of inequality as before, then the manifold has strong restrictions. But the problem is there some other type of inequality on a complete manifold with a non-negative rich curvature? So we can't expect a Sobolev type of inequality as before to hold on a general manifold with a non-negative rich curvature. But now if we pick a complete manifold with a non-negative curvature, we also still hope to find some other kind of inequality. Okay? Then we look at the Hardy and Rellich type inequalities. So this is the classical Hardy inequality here. The Hardy inequality was extended to this the form by Rellich. This is the so-called Rellich inequality. Okay. We look at also the best constants in these two inequalities here are exactly these two constants, and so the best constant, so the inequalities before are best possible. And then we look at this result by Cajon. He hopes to prove a hard type inequality. So we have a complete manifold, complete open manifold. And then this inequality holds. Here, the weight function law has has gradient which has complement 1, and the Laplacian of this function is not less than this function in the sense of distribution. And then the numbers here, alpha c, satisfy these two conditions here. So the conditions here are satisfied by the Hadamard manifold. So this means that on a Hadamard manifold, if we take rho to be the distance function, then we have this Hardy type inequality on the manifold. Okay. Also, this result has been extended by Combe or Zadin in 2009, which to the power p here. So in the Cajon's theorem, here is the square, and then in the result of Combe or Zadin, here is the p. Also, Rellich type inequality has also been proved by them. So this means that they considered the case of manifolds which are more general than the Hadamard manifold, but the manifolds with non-negative Ricci curvature are not included in their results. Okay, then we consider the manifolds with a non-negative Ricci curvature. So on a manifold with a non-negative Ricci curvature, the distance function satisfies these two inequalities. Here is less than or equal to in the sense of distribution. Okay, then we prove some Hardy type inequality on a manifold supporting a function of this type. We assume that on an open manifold which supports a function rho satisfying these two conditions here. And then for any function phi in this space, we have this inequality. This is a Hardy type inequality. Then we can also prove some similar results. For example, we have we put a p here. So the result before result which is a little bit different. We have this. Also, we have the condition here. So the manifold with a non-negative Ricci curvature are contained in the result. So this is a stronger version of the Hardy type inequality. So we have a complete manifold, and we have a bounded domain which is a smooth boundary in M. We have the numbers here satisfying the conditions here. If we take a function in this space, then we have this inequality. This is this inequality is a little bit stronger than the inequality before, since we have two terms here and two terms here. Then we have a Rellich type inequality for manifolds supporting a function which is something like the distance function. So we have Laplacian of phi square. The integral here is not less than this integral. This is the Rellich type inequality, and then an improved Rellich type inequality. There are many things to state in the result. We have conditions here, numbers here, and so on. But it is just an inequality which is similar to the improved Rellich inequality in the Euclidean space. So that means that on a complete manifold with a non-negative rich curvature, we can prove some Rellich, Hardy and Rellich type inequality. I think so. This is I think that there should have some things more to do about manifolds supporting a function which is similar to the distance function on manifold with a non-negative rich curvature. Okay, so I think that's all. Thank you very much.